All right, first of all, are there any questions? And I didn't retrieve any minute questions on Monday, so I don't know what to say. So today we want to say some more things about central potentials and then get started on the hydrogen atom. I was thinking of reviewing some of the central potential material. Is that a good idea, or is that stuff that you've seen so many times you just couldn't bear to see it again? Come on, give me feedback.
Like which central potential in particular?
Or in other words, equations like this. Now, this has various brothers and sisters and daughters and sons. Do you want to see this again, or is this stuff that you've seen so many times? So this is the main part of the kinetic energy operator. This is the relative momentum. This is the eigenstate of position operator. This is any old state. This is the angular momentum operator. And we know that we can set psi equal to some quantum number or numbers n, Lm, and for now we're ignoring electron spin, and we know that we can have L squared on n Lm, of course, is h bar squared L plus 1 n Lm, Lz or L3 n Lm is h bar m n Lm. And we know this from the general theory of angular momentum, which we've been through. We also know that R, well, I might as well finish it since I've gone this far. R L squared NLM is minus h bar squared 1 over sine squared theta d phi squared plus 1 over sine theta d theta sine theta d theta, all that acting on R and Lm. And of course R, we're going to be using spherical coordinates, and so our state R is going to be length of R theta phi. Okay, this is all right. We also, all right, a couple more review things. R theta phi Lz NLM is h bar over I d phi of R theta phi NLM. And this R theta phi NLM, we're going to be writing as R of NL of R, and then Y Lm of theta and phi. And I guess just to cut this short a little bit, Y Lm of theta and phi is, let me just say it's a, first of all, minus 1 to the m, a big square root of 2L plus 1 over 4 pi, L minus M, L plus M, factorials, and then TLM of cosine theta and e to the IM phi. So that's the whole structure of it. So the angular part is completely standardized. These horrible square roots. The square root is for normalization. What we want is that an integral d phi from 0 to 2 pi, integral minus 1 to 1 d cosine theta of y L prime m prime of theta and phi, complex conjugate y L m of theta and phi should be delta L prime delta m prime. So that's the reason for the crazy square root. Minus 1 to the m is there for, I forget, there's some other technical reason why one adds a minus 1 to the m. Any questions about that? All right, let me just say something about the PLMs. First of all, is this Rodriguez formula. PL of x here, x is cosine theta. PL of x is minus 1 to the L over 2 to the L factorial, the Lth derivative with respect to x of 1 minus x squared to the L. So that's the Legendre polynomials, but these guys are the associated Legendre polynomials, and they differ by PLM of x is 1 minus x squared to the m over 2 dm dx to the m of PL of x. So now you have the whole 9 yards. In any event, the angular stuff is codified here. P0 of x, of course, is 1. P1 of x is x. P2 of x is a half. 3x squared minus 1. P3 of x is a half. 5x cubed minus 3x. So you see the odd ones are odd in x. The even ones are even in x. So in other words, Pn of minus x is minus 1 to the n Pn of x. The y's are pretty simple also. Y00 is just 1 over the square root of 4 pi. That's so that you have the normalization, right? Y10 is square root of 3 over 4 pi cosine theta. Y plus or minus 1 is minus or plus square root of 3 over 8 pi sine theta e to the plus or minus I phi. Notice that if x is cosine theta, 1 minus x squared is sine squared theta. If you raise that to the power m over 2, it's just sine theta to the m. So that's why these funny factors occur. Y20 is square root of 5 over 16 pi, 3 cosine squared theta minus 1. So the Y0s are essentially just the just the Legendre polynomials, and then the y's with different values of m have these phase factors, EVIM, phi, and also you differentiate and multiply. Okay, so that's basically that. Now the equation, I guess I'm going to write it backwards. E NLM take the inner product here with r theta phi, r theta phi, almost invisible. What we get here is E and L, R and L of R, Y L M of theta phi. And now in here what we have is r theta phi, E squared over 2m plus B of R, NLM. And then this kicks in a derivative, second order derivative with respect to R, and then an L squared term. And then we still have the V. And so altogether this becomes minus h bar squared over 2m r squared d by dr, r squared, and then r prime nl, and then y lm. This thing is of r, this thing is of theta and phi, and then plus h bar squared l plus 1 over 2m r squared r nl of r ylm theta phi, and then finally v of r times r nl of r y lm theta phi. So that's that eigenfunction equation just becomes this. And what you notice here, this r prime just means derivative of r and l with respect to r. YLM then is a common factor, and you can cancel it. And so the equation you get is ENL RNL is minus h bar squared over 2m r squared, and this becomes r squared r prime and l prime plus h bar squared l plus 1 over 2m r squared plus v of r and l. So that's the equation. So this is then a second order ordinary differential equation, and that means that one can use various techniques for solving it. Typically what you do is you use the method of, God, the name has just gone out of my head. It's on a couple of pages down. The method of, may not even be in these notes, maybe I'm running out of notes. Anyway, you use a series solution. So we can basically say R and L of R is some R to the C0, and then a sum R, so R to the N, Cn, N equals zero. Okay, so we're going to do that later. We'll do that explicitly for the hydrogen atom. Anyway, that's what you basically do at some point. So it's in general hard to solve this, but you can always find a series solution, and at least if the potential isn't too crazy. Notice that what we have here is effectively an effective potential. The effective potential, that's an E. Actually, it should be an L. Let's call it an L. VL is V of R plus H bar squared L plus 1 over 2m R squared. So there's what effectively you have is a one-dimensional problem with a different potential. The potential is the ordinary potential V of R, and then augmented by this centrifugal barrier. And so this thing looks like looks like this. If you have L equals 0 and V is an attractive potential, then the thing looks like this. But then the L equals 1 does something like that, and L equals 2 does something like that. So that's L equals 2. This one is L equals 1, and this one is L equals 0. And unless the potential is really crazy, this term, as R goes to 0, is dominant. So this dominates at small r. And so consequently, this barrier here is such that what I'm drawing here is V sub L of R. And that potential prevents the particle from getting to the origin unless L is equal to 0. So the particle is kept away from the origin, except for L equals 0. What I've drawn here is actually the way it looks for the case V of R equal to minus E squared over R, which of course is the hydrogen atom potential, in suitable electrical units. Now, this equation up here simplifies somewhat because 1 over R squared, R prime, you can multiply that out and get 1 over R squared, 2R, R prime plus R squared, R double prime. And then that's the same thing as 1 over R, 2R prime plus R double prime. And that's the same thing as 1 over R, big R, double prime. And that's a neater way of looking at it because in these terms, then the radial equation is minus h bar squared over 2m, 1 over r n l, double prime, plus, in fact, why don't I just make it forward simpler, just like this is VL of r n l is equal to E n l, r n l. The reason that E depends just on N and L and not on M is that it's a central potential. In the case of hydrogen, it doesn't depend on L either because of the hidden symmetry. Okay, so that's that equation. And in fact, a nicer way of writing this is, unfortunately, I don't do this until the next page, but you can see immediately that this, if you multiply through by R, then this equation becomes, and you let R big R equal to U, then this equation is minus h bar squared over 2m U double prime plus R V sub L. Oh no, that just becomes, forget the R, it just becomes V sub L U is equal to E n L U n L. So in other words, multiplying through by R and identifying R, big R, as U, you get a simpler differential equation. And this is the one that one actually, when one is serious, one actually solves that equation. And that looks much nicer. Now it really does look like a particle in one dimension. The only difference is that only R greater than or equal to 0 counts because R is the absolute value of the distance, the absolute value of the separation between the two particles. And so you don't have any negative R. And moreover, you're protected from that puzzle by the fact that this keeps you away from negative R. Okay. I'm going to depart slightly from the notes here, so you need to watch me like a hawk, like four hawks. Okay? But I think it makes it a little bit simpler. Let's look at this behavior for small r. Well, for small r, what we have is minus h bar squared over 2m u double prime. That's going to be important. And then over here, we're going to have plus h bar squared l plus 1 over 2m r squared times u equals 0. So this is going to be what the equation is going to look like at small r. And if we cancel the h bar squared over 2m, we have minus u double, or we can just say u double prime is equal to l plus 1 over r squared u. And now we can say let u equal to r to some power, say s. Well, then the left-hand side is s minus 1, r to the s minus 2 is equal to l plus 1 over r squared, r to the s. Or in other words, the r's cancel and you get s minus 1 equals l plus 1. So that's a quadratic equation. It's clear that there are two solutions. If you said, all right, hold it, I've done something wrong here. Well, all right, it's just that I'm using a different, I'm departing from the notes, and so I'm using a different thing here. What we can say here is that s can be equal to l plus 1. If s is equal to l plus 1, this is a solution, right? Okay? Because the other solution is s equal to minus l. But this is a singular solution. And so we're not going to take that solution. So s equals, so u n l of r goes as r to the l plus 1 as r goes to 0. All right. That's a general rule then for these equations. It's not quite general though, because what I used here was that these are the two dominant terms in the equation. These are the two dominant terms in the equation as long as L is not equal to 0. If L is equal to 0, then this argument that I've gone through here doesn't make much sense. So for L equals 0, you have to examine you have to take it, you have to look at the potential and analyze this equation for the whole equation. You analyze this equation in the limit of r going to 0 to figure out what happens for L equals 0. In the case of hydrogen, it turns out that this is true even for L equals 0. Okay. Now, what about at large distances? Well, we have this equation, and at large distances, these terms are going to 0 quickly. This term goes to 0 as r goes to infinity is 1 over r squared. And moreover, the potential presumably falls off also. These are central potentials and they fall off with distance at some power of r. So that's gone. And so the actual equation as in the limit r goes to infinity, the equation up here becomes simply this equals that. And so that becomes minus u double prime n L is equal to simple solutions to this. There are, of course, two solutions. One is a growing exponential, one is a decaying exponential. The growing exponential is crazy because it's, just completely unnormalizable. And so the solution is UNL of R is e to the minus square root 2m ENL over h bar squared, all that times R. So then you differentiate once, and, well, sorry, there's a minus sign in here. You differentiate once, and you get, sorry, let me just show you. U prime then is minus the square root times u. U double prime is the minus the square root squared times u, which is minus 2m e over h bar squared times u. So that satisfies this equation. It just has a minus sign on the opposite side. So the behavior, as long as E, so here, I'm going to write this, as long as we're talking about a bound state, so the ENL is less than 0, then as R goes to infinity, the solution is this one here. UNL of R is e to the minus square root minus 2m e over h bar squared. That thing's positive since e is negative times R. Again, apart from, I'm giving you the dominant behavior, not the, obviously this gets multiplied by a polynomial, so this is up to a polynomial. So in other words, what we have then is the UNL of R goes as e to the minus 2m ENL, we don't know what that is yet, over h bar squared times R, as R to be L plus 1, at least for L greater than 0, and this is R goes to 0, and this is L goes to infinity. Okay, so those are the asymptotic behaviors of this function U. We can look at the particular case of, any questions? Remember, I have a candy. I don't think I'm running on chocolate, but I do have candy to reward questions. Okay. Let's look at this more carefully for the case of the Coulomb potential. That's the next topic. So suppose V of R is minus e squared over R. So then what we have is minus h bar squared over, that's a square, over 2n. U double prime. And we're looking at L equals 0, so n 0. Minus e squared over R, un 0, equals en 0, un 0. Notice the L plus 1 term is gone because I'm setting L equals 0. All right. So, what does this look like near R equals 0? Well, near R equals 0, we can forget this term. We just have the equation. So what we do is we say, let U equal C1R plus C2R squared. And then the equation becomes minus h bar squared over 2m. The second derivative, well, the second derivative of this is just 2c2. And then that's supposed to equal, if I put this over to the other side, e squared over r times c1r plus c2r squared. Well, in the limit of r going to 0, that says that C2 is equal to minus m e squared over h bar squared C1. And notice that we have here, this is a second order equation, so we expect to, well, this is just the beginning of a series solution. But the point is that our series solution is such that it starts at r, the first power of r. And so consequently, u n 0 of r goes as r, simply as r. And that is r to the 0 plus 1. So as I said, the case for the case of hydrogen is one in which you can ignore this caveat. So you might as well do hydrogen now. Are there any questions? All right, let me remind you though, this is something that is often skipped in these analyses, and I think it's a little bit too bad. The Hamiltonian for the electron-proton system is p electron squared over 2 mass electron plus p proton squared over 2 mass of proton, and then minus e squared, again in these units, r sub e minus r sub p. So that's our that's energy for the hydrogen atom, and the units that we're dealing with are ones where e squared over h bar c is called the fine structure constant, and it's something like 1 over 137.036, because it's known better than that. There are at least 3 systems of units in current use. One of them has e squared over 4 pi h bar c over 1 over 137. One of them is this one, and the other one is the one that it's the worst case. It's the one that has epsilon 0 and so forth. I don't know, it would have been so much nicer to take these electrical units and combine them with meters and kilograms if you want. But unfortunately, it didn't. Anyhow, so what we're going to do is what we did when we analyzed the two-body problem, namely we're going to say the total momentum P is PE plus PP. The total, the center of mass is MERE plus MPRP over ME plus MP. The separation is RE minus RP. And the relative momentum, this is the weird one, is MP times PE minus ME times PP divided by, divided by big M, where big M, of course, is ME plus MP, and the reduced mass, mu, is ME MP over M. So those are the conventions that we introduced when we were dealing with the two-body problem. And one of the homework problems that I added was that this Hamiltonian, in terms of these variables, can be written as HEP equals P squared over 2 big M plus relative P over 2 reduced mass minus E squared over the separation, where here R is the absolute value of R e minus R. And now we can have eigenvectors of all of these bunch of operators here. In the notes, for some reason, I chose p squared as one of the operators that I would have an eigenvalue of, but that's something that's kind of silly. So our eigenstates are going to be p prime NLM, and they're going to be eigen vectors of the total momentum NLM, and then also of HEP, and this will be p prime squared over 2m plus what we're going to call ENL, p prime NLM, and then of course L squared on this state is H prime squared L plus 1 on the state, and LC. L3 can be H bar M on the state. And when I say L squared and L3, remember for this problem, L is equal to R cross P, R cross big P, plus R cross little p. That's the total angular momentum. That's L, let me call that as LEP, and I'm going to write that as R cross P plus L, and so it's this L that we're talking about here, just the relative orbital angular momentum. Remember, you can solve in general for R. R goes as some R of 0 plus T times P over M, and P prime, which is this eigenvalue. And so consequently, this thing is a constant because P prime crossed into P prime gives you 0. So this is just a constant overall angular momentum. Okay, so what we're going to be doing then is these things are direct product states, and we're going to be writing this as P prime direct product NLM, and then we're going to just ignore the overall translation of the total atom, and so we're going to separate the HEP as P squared over 2 big M plus H, and then H is P squared over 2U minus E squared over R. So this is the thing that we're going to actually analyze. And we're going to analyze it the same way we did over there. Namely, I'm going to skip a couple of lines in this text. R, NLM. So maybe I should do this a little bit more. Go back to the two-body state for a moment. Big R, comma, little r on P prime NLM. This is going to be big R P prime times little r NLM. This thing is going to be e to the I r dot P prime over H bar divided by 2 pi H bar to the 3/2 times this thing, and this thing is going to be R NL of R Y LM of theta mu t. So I'm borrowing all this stuff we did for the two-body problem earlier in the lecture. So this is the structure that we've got. And the equation over here, the one in the box there, that equation in the box I can reproduce here, are only a foot tall. 2 feet would be even better. Anyway, it's going to be minus h bar squared over 2 mu double prime and of r plus minus e squared over r plus h bar squared l plus 1, 2 mu r squared, that's a mu. UNL over R equals E and mu. Of course, I'm writing E and L, which is stupid because we know that it doesn't depend upon L because of the hidden symmetry in the hydrogen atom. We're going to change variables to R equals to rho times A0, where A0 is the Bohr radius, which is h bar squared over mu e squared, which is 0.529177 angstroms. So it's basically half an angstrom or 5% of a nanometer. So this is the Bohr radius. And then we're going to write UNL of R equals to V and L of R over A0, which is to say VNL of rho. And that means then that U prime NL of R is V prime times V prime of rho times rho prime. That is to say, the derivative of rho with respect to R. And rho is R over A0. And so this is V prime of rho divided by V0. And that means that when we do this up here, we're going to get 2 factors of A0 here. U is going to turn to V. We're going to have 2 factors of A0. And then, well, let me go over here and give you the whole shtick. It's minus h bar squared over 2 mu A0 squared V double prime. Let me leave off the subscripts on the V. Plus, and this is V double prime of rho, minus E squared over A0 rho, that's what R is. And then h bar squared L plus 1 over 2 mu, and R squared is A0 squared, rho squared, V equals EV. Okay. So that's the equation, and now we get to cancel a lot of these constants. Do you guys want some of these crackers? Yes, no? Maybe? All right, so what happens here is we have minus h bar squared over 2 mu squared e to the 4th over h bar to the 4th v double prime plus minus mu e to the 4th over h bar squared rho plus mu e to the 4th over 2 h bar squared rho squared L plus 1. I see this. See what I did. All right, let me tell you, this is a pedagogical mistake on my part. I decided I wanted to change the name of U to something else, so I picked V. That, of course, was dumb because we had V as the potential. So, I'll call it W. U goes to W. Oh, but there isn't any, V is gone, so maybe we could stay with V. Because V is minus E squared over R, and we don't have the V anymore. So so I keep it with V? All right. Okay, well, that's the equation there. And if we define the ionization potential as mu e to the fourth over h bar squared, actually over 2h bar squared. This can also be written as a half mu c squared alpha squared, since that's a half mu c squared, and alpha squared is, alpha is e squared over h bar c. And so then this is squared, and so you can see you get the c's cancel, you get the h bar squared, and you get the e to the fourth. So this is a nice way of thinking about this. This is mu c squared is the relativistic rest energy associated with the rest mass of the reduced mass of the electron. Alpha squared is 1 over 137 squared, so that's a reduction of the energy scale by 2 factors of alpha, which altogether gives you something less than 10 to the fourth, and then you have a factor of 1/2. This is altogether something like 13.6 electron volts. If we do that, then we can rewrite this equation as minus EI V double prime plus EI L plus 1 over rho squared minus 2 over rho EI V equals EV. So that's the way, that's one way of writing it. And now we see that this EI is almost a common factor. And so if we cancel it, what we get is V double prime plus 2 over rho minus L plus 1 over rho squared times V is equal to what I'm going to call lambda squared V, where lambda squared is minus ENL over E sub I. So this is the, ENL is negative, that's the binding energy. Minus EL then is positive. EI was explicitly positive, so lambda squared is positive. So this is the equation then that we want to crank down on and actually get an exact solution. Any questions? Frobenius, by the way, is the name that I was looking for. All right, so that's the differential equation here. And let's again look at what does this look like as rho goes to infinity. Well, obviously, it looks like V double prime is, let me just say, is lambda squared V. And so one solution is V of rho is equal to Y of rho times e to the minus lambda rho. And this, what we're going to do, in other words, is we're going to take out the overall exponential behavior. And so then you have V prime is Y prime e to the minus lambda rho minus lambda y e to the minus lambda rho, and that is y prime minus lambda y e to the minus lambda rho, and then you get that b double prime is y double prime minus lambda y prime e to the minus lambda rho minus lambda times y prime minus lambda y e to the minus lambda rho, and this thing is all together y double prime minus 2 lambda y prime plus lambda squared y e to the minus lambda rho. Okay. So that's what that is. And we can then put this expression for b double prime, we can put in this equation, and then the expressions for v as y e to the minus lambda rho. And then what happens is one of the terms cancels. This lambda squared v is going to cancel because v double prime gives us a lambda squared v. And see, I'm trying to do that without erasing another board. I guess I'm going to have to. So let me write down the whole equation here. It's y double prime minus 2 lambda y prime plus lambda squared y e to the minus lambda rho plus 2 over rho minus L plus 1 over rho squared y e to the minus lambda rho equals lambda squared y e to the minus lambda rho. So, as promised, this term cancels this term. And then after that, there's a common factor of e to the minus lambda rho. And so when we're done, what we have is y double prime minus 2 lambda y prime plus 2 over rho minus L plus 1 over rho squared times y equals 0. Because y is y and L, and in fact it's really just yn. Well, it might be 1 L actually. E is going to be just en. Okay, so that's the expression. Now we use Frobenius's trick, which is y is going to be rho to the s times the sum CQ rho to the q, and here q is 0 to infinity. So that's going to be our formula. And remember, the key here is that C0 is not equal to 0. That's what makes this, fixes the definition of S. And so this tells us here that y is rho to the s as rho goes to 0. And we can see that what that means is that y here is essentially at small r, y is essentially u, and u goes as what is it, y to the l, I mean r to the l plus 1, right, r to the l plus 1, and so we expect here that S is going to be equal to L plus 1. That's at least what we expect. In any event, y prime is a sum, S plus Q CQ rho to the S plus Q minus 1, and Y double prime is a sum S plus Q minus 1 CQ rho to the S plus Q minus 2. So that's just differentiating the power series. Okay, so now I'm going to have to erase this board and get the rest of this done. Okay, so what? So what we do is we take these three equations and put them into that equation. And what that gives us then is sum over Q, S plus Q, S plus Q minus 1, CQ, go to the S plus Q minus 2, minus 2 lambda, sum over Q, S plus Q, CQ, go to the S plus Q minus 1, plus 2 sum CQ, rho to the S plus Q minus 1. That's the Coulomb term. And then minus L plus 1, sum CQ, rho to the S plus Q minus 2 equals 0. Right. Notice that the term that really has the energy in it has disappeared, except for a remnant right there. Okay, so now what we do is we look at this, we examine this equation in the vicinity of r equals 0, something we've already done several times, in order to obtain the initial equation, which tells us what the value of S actually is. And so the terms that dominate are the terms that have Q equal to 0. And so what we have then is S minus 1, C0, rho to the S minus 2, minus L plus 1, C0, rho to the S minus 2 equals 0. Those are the two dominant terms coming from here. You see this one, if you set Q equals 0, you only have rho to the S minus 1, which isn't as important, and the same thing for here. So these are the dominant terms, and this tells you then that S minus 1 equals L plus 1. Well, that's the equation that we obtained over there, and that tells us that S is equal to L plus 1, or S is equal to minus L. This is crazy because it's so singular, and S equal to L plus 1 is the one that we anticipated from the previous analysis. So now we actually know what's happening, namely that this Y, NL of rho, is rho to the L plus 1, sum on Q from 0 to infinity of CQ rho to Q. All right, so this recapitulates what we learned earlier. Now, the next thing to do is to shift the indices in this equation so that the same power of rho occurs in every term. And once we've done that, we can then set the coefficient of that common power of rho equal to 0, and that will give us a recursion relation, which will allow us to determine the whole power series. This is the whole strategy of Frobenius. So when we do that, this becomes the following. Sum Q equals 0, L plus 1, I've set S equal to L plus 1, plus Q, L plus Q, CQ, rho to the L plus Q minus 1, minus 2 lambda, sum Q, L plus Q, CQ minus 1, rho to the L plus Q minus 1, plus 2, sum CQ minus 1, rho to the L plus Q minus 1, minus L plus 1, sum CQ rho to the L plus Q minus 1 equals 0. Okay. So setting the coefficients of each power of rho, now that we have a common power of rho to the L plus Q minus 1, what we have then is L plus 1 plus Q times L plus Q minus L plus 1 CQ is equal to 2 L plus Q lambda minus 1 CQ minus 1. Okay, well that can be simplified somewhat to L plus 1 Q plus QL plus Q squared CQ equals 2, and then the same thing, L plus Q lambda minus 1 CQ minus 1. And you can factor out a Q from this, and so you get 2L plus 1 plus Q times QCQ is equal to 2 L plus Q lambda minus 1 CQ minus 1. Okay, so that's the recursion relation. Now, with that recursion relation, what does this tell us? Well, it tells us in particular that as Q goes to infinity, CQ is approximately 2Q lambda CQ minus 1 over Q squared, or 2 lambda over Q CQ minus 1. That means that roughly CQ is going as 2 lambda to the Q over Q factorial times C0. This is just a large Q behavior, not the exact behavior. And that means that Y is going as E to the 2 lambda rho. So that's crazy behavior, because it would dominate the exponential behavior, the damped exponential e to the minus lambda rho by it's going to rise twice as fast as that decreases. And so this is something that is a disaster to be avoided. Okay, so how do you avoid this? Well, as usual with the method of Frobenius, the way to avoid a disaster is to say that this recursion relation at some point tells you that CQ is 0. And in that case, this sum never goes to infinity and this disaster never develops. And so that's the way out. And so now we have to see, well, how can that recursion relation avoid this thing going to infinity? In fact, it brings to my mind the bailout, the sums used for the bailouts. Very disturbing. Anyway, so what we want, you see, is the C cubed, which is 2 times lambda plus q, L plus q, lambda minus 1 over 2 lambda plus 1 plus q times q. See, q minus 1 is 0. Well, it's pretty clear how to do that. You just want that for q equal to k, some integer, lambda plus k, L plus k times lambda is equal to 1. Or that lambda, now I'll put in what lambda is, and lambda sub nl is 1 over L plus k. Okay, so that gives us the termination. And now we remember that, in fact, lambda squared, and in fact, this L plus k is what we're going to set equal to n, the principal quantum number. Principal quantum number. So lambda squared then is 1 over n squared. And then E and L, remember, is minus EI over lambda squared, times lambda squared. So it's E sub I over n squared. This thing being 13.6. So this is minus 13.6 EV over n squared. And as foretold, because of the hidden symmetry, it doesn't depend upon L. Because of the rotational invariance, it doesn't depend upon M. Okay, so that basically is that. Is there a question here somewhere? So how does this work? K, let's just, we're out of time, so let me just say a couple of words. Namely, what is this K? K is greater than 0. It's an integer greater than 0 because it's a value of Q. Q starts with 0. The thing can't terminate on the first term. The whole function is 0. So that means that L, which is n minus k, then L could be 0 and is less than or equal to n minus 1 because k can't be any smaller than 1. So L runs from 0 to n minus 1. All right, I think I'll stop at this point, and next time we can go over. I'm going to post these solutions tonight, since the 4 of you have turned in the homework, and I'm afraid the 5th students don't have turned in them all, so I'll just post the solutions. Are there any questions? This was worked out almost 100 years ago by Bohr, but not using this complicated theory. It was, I guess, about 80 years ago when Heisenberg and Schrodinger worked this out. Schrodinger he was using the wave function. So I guess if there's no question, just end the you know how to put it onto the stick?
I don't
There's a
remember.
memory stick in the back there. If you don't know how to do it, I'll go